Hi everybody, welcome to our new video. Now, in the previous video, we discussed about the Laplace transform, okay? So we explained why it is so useful in studying and solving differential equations, okay? And now we're going to start by describing some very simple examples of solving systems of differential equations, okay? Now, when we are solving a system of differential equations, there are two, I would say, basic types of solutions. Now, first of all, when I say a solution, you will often hear me say a response, okay? So we say the response of a system. By that, we practically mean the solution of the system, okay? So response and solution is pretty much an identical term. Okay. Now, we categorize the solution or the response, if you like, depending on whether we are starting from zero initial conditions uh, by having some input to the system. So let's say at time zero, the system is stable, is relaxed, is not moving at all, and we apply an input, okay, that we provide ourselves, so an outside input. When we have this sort of differential equation, the output is called the response of the system or the forced response of the system. Okay, and why do we say forced response? You will also see it as dynamic response. Okay, we say it forced response or dynamic response because we refer to a system that starts from zero, okay, but has some input applied into it. Okay, now on the other hand, when we have the solution of the system that doesn't have any input put into it, but starts from a non-zero initial condition. So let's say at time zero, let's say I have a spring mass system that, is like that stable, and at time zero, I pull it down, okay, from a non-zero initial condition, and I leave it free, and I see how it responds. Okay. I see what's the response, to that specific initial condition. Okay, and this solution is called in Greek, we call it free response, but you will also see it mentioned as an unforced response, meaning the response under no outside force of the system. Okay, so we have this categorization of forced responses and unforced responses. Okay, so let's begin by having some very, very simple examples of these two responses. Okay, so let's begin by simple differential equation. Let me write it down right here. All right, what's that? 3 times x of t equals 0. Nice. And the initial condition for this system is x0 equals 1. Okay, so there is no input to the system. Okay, the system starts from a non-zero initial condition. So at time 0, I move it from the equilibrium, okay, at position 1, and then I see how it behaves. Okay, so this is time, okay, and the system at time 0 begins from this part right here, from position 1, right? So let's solve it. Actually, solving it is very, very easy. What are we going to do? Well, of course, we are going to apply Laplace transform, pretty much like we discussed earlier. So let's see what happens. Okay, so the Laplace transform of this whole equation right here, let me write it analytically, is the Laplace of 0, of course, on the right hand. And let's see what happens. Remember, Laplace transform is linear, so it goes into each individual term in this summation. So it has I'm sorry, is s times x of s, which is the Laplace of the function under study, minus x0, nice, plus 3 times x of s. This equals 0, right? So now we are going to factor these two terms together. So let's see what happens. We have s plus 3 times x of s, and this is equal to 1. Let's put it on the right-hand side. Nice. So now what are we going to do? Of course, we need an expression for x of s, okay, which is the Laplace of our function. So I'm going to move this factor down below on the right-hand side, giving me 1 over s plus 3. Nice. Simple as that, right? So what do we do now? Well, if you go back to the previous video, you will remember that, well, uh, for this term right here, we already have the Laplace transform, the inverse Laplace transform, right? So that's the whole idea behind the Laplace transform and why is it so useful. You take a differential equation, you apply the Laplace transform, okay? You get this sort of expression right here. You factor all the terms for x of s, right? Everything else you move to the right side, and then you get an expression for the Laplace transform of s. And then the only thing I need to do is take the inverse Laplace transform, because the inverse Laplace transform will give me the solution, okay, with respect to time, so x of t, and let us remember the inverse of this one, of this term. The root here is, if I set this equal to 0, the root is -3, right? So we have an exponential function of -3 times t multiplied by the step input, because we start at time 0, right? So this is it. This is our solution to the system, right? Simple as that. Congratulations, you have just solved your first differential equation, right? So great. Now, let's see. Is the solution correct? Well, if I put x of 0 right here, the solution that I'm going to get should be the same as the one given by the exercise. And indeed, we would have epsilon to the minus times u of t, which gives us 1 at time 0. So indeed, the system starts from position 1. If I got a different result, probably I would have made a mistake. Okay, and how does this function behave, I'm sorry, as stuff goes to infinity? Well, this is very easy to understand. This is just a simple exponential function. We don't have any oscillations here, so it simply goes, I'm sorry, to 0 steadily but surely, right? So this is a solution. We have a system starting from time 1, I'm sorry, from position 1 at time 0, and then slowly going towards the 0 state, right? So the system goes to 0 as time goes to infinity. So this is a simple example of a so-called free response or unforced response, okay, because we don't have an input. Great. So now let's see an example of a forced response, right? So let's clear this canvas and let's take, all right, I'm going to take the exact same differential equation. Nice. But now I'm going to give it an input as well, okay, where u is a step input. Remember, I generally use u to denote any type of input. So unless otherwise said, don't assume that u is a step input, okay? The exercise must tell you specifically that we are talking about a step input, right? And the system starts from 0 initial conditions. Okay, so what I'm going to do, I'm going to do here. The response that I'm going to find is called either dynamic response, all right, or a forced response, depending on the book that you will read. Now, specifically, since here we have the step input, we can also call the solution step response, all right? So a step response refers to an output of the system under a step input and always starting from 0 initial conditions. Okay, so if you hear step response, we mean 0 initial conditions. So let's begin. We have s, oops, again, I'm sorry, s of x, s minus x0 plus 3 times x of s equals u of s. Nice. This, of course, is 0. So let's factor all the terms together. S plus 3 x of s equals u of s. Nice. And then we need an expression for x of s because that's the function we're trying to find. And this becomes u of s over s plus 3. And of course, this is the step function, and the step function has a Laplace transform of 1 over s. So this becomes 1 over s times s plus 3. Nice. So all is good up until here. We got an expression for the Laplace transform of the function x, right? But here we have our first problem, which is not actually a problem. Because you're thinking, you know, Lazarus, I mean, I have the book right here. It has a very big table of Laplace transforms for step input, for exponential functions, for cosine, for whatever. It doesn't have an expression for this thing right here. Okay, this is a polynomial on the denominator. But if we look on all our tables and our previous videos, you will not find, a formula for this rational function right here. So we are stuck, right? Actually, no, we are not stuck, and this is why the Laplace transform is so extremely useful. Because using some very basic mathematics, I would say elementary mathematics from secondary education, we know that a function that is a rational function like that, so a fraction that is a polynomial here on the denominator, can be actually broken down into individual fractions. And this procedure is called a partial fraction expansion. So once the denominator is factored into these individual terms, this fraction right here is equal to the summation of the individual fractions, right? So why is this useful? Well, look at that. I don't know the Laplace transform of this, right? I have no idea what is the Laplace transform here. But I know the Laplace transform of this term, and I know the Laplace transform of this term, right? And this is why the Laplace transform is so extremely useful, because even if here I had a polynomial on the denominator of like 10th order, 15th order, 20th order, 100th order polynomial, I don't care. I can compute the roots of the polynomial, factor it, break it down into 10, 15, 20, 100 individual fractions, and for each individual fraction, I know the inverse Laplace transform, right? So this is why this is an extremely useful solution. It can work with any type of fraction and differential equation, no matter how big it is. Okay, here we have a simple one, but even if it was much bigger, the procedure would be exactly the same, right? But before we proceed, we just need to compute this value A and this value B. Okay, so how do we do that? I mean, if you know from secondary education, you can actually put these hats right here and go into the procedure of finding A and B, analytically. But there is another formula that is very, very simple, and that's the one that we are going to use. I'm going to explain this here, and it is very easy to understand. For the factor A is the limit, let's see, well, S goes to what? What's the root here? 0. So S goes to 0 of S, which is the term right here, multiplied by this fraction right here, 1 over S times S plus 3. We remove this term. Okay, so now we have 1 over 3, right? So this is the very, very simple way to compute the factors. And you can understand that we have a very similar process for beta. So let's see. It's the limit of S goes, what's the root right here? S plus 3. If we set this to 0, the root is minus 3. So S goes to minus 3 of S plus 3, we have the exact same term over this fraction right here. 1 over S times S plus 3. So this goes, this goes. So now we have 1 over minus 3 or minus 1 over 3, right? So that's the process. As you can understand, it's very, very simple. For different types of roots, it gets a bit more difficult, but in this very simple case, there is no difficulty in computing these terms. So let's put an asterisk right here, and let's rewrite this. And we have that x of s is equal to 1 over 3 of 1 over s minus 1/3 of 1 over s plus 3. And this is great because now we can take the inverse Laplace transform and obtain the solution of the system. Because now, oops, I'm sorry, x of t is equal to 1/3 times the step input minus 1/3 times epsilon to the minus 3t on the step input, right? And this is it, right? We didn't need anything else to obtain the solution. See how simple it is? So no matter how big the differential equation is, we take the Laplace transform, factor the common terms, we will obtain some sort of rational function here with some polynomial in the denominator. We factor the polynomial, do this partial fraction expansion where we break down this big polynomial into individual terms, compute its individual factor, a, b, c, d, no matter how many they are, and then we simply take the inverse Laplace transform and have the solution of the system. Okay, simple as that. So this is the forced response of the system, and let me plot it right here. Oops, I'm sorry. All right. Don't want that. Let's go back. So, all right. So this is time, and the exercise told us that we are starting from zero initial conditions, which indeed holds true because if I put here x of 0, I will simply get 1/3 minus 1/3 equals 0. So actually my solution is the same as the value that the exercise told me, right? If I got a different solution right here for time 0, this would mean that I would probably have made a mistake. Okay. So how does this function behave as we move to infinity? We have two terms. Okay. This term goes to 0, right? This term is stable. So they cancel out each other at time 0, but over time, this term will diminish and this term will stay. So eventually the system will start from the 0 position, and without having any sort of oscillation, it will stabilize on this 0 position right here. So that's the solution of the system, right? It starts from 0, and just because we are giving it some stable sort of source of energy, it will not end up in the 0 position, but it will end up in a non-zero position, which is 1/3. So this is the dynamical response or the forced response or the step response, if we want to be specific, right? So this is it. Unforced response and forced response, right? So now let me end up with the last question, which is what happens when we have both types of, I'm sorry, both types of responses. And by that, I mean, what happens when we have, let me, right, just a moment. All right. So what happens when we have a system that is driven by an input? So let's say we have the same differential equation. The system is driven by a step input, but at the same time, the initial condition is not 0, but it is a non-zero value, right? So in this situation, the response is called usually the complete response. Pretty much that's how we say it in Greek. And this response actually, due to the fact that the system is linear, this response is actually the summation of the previous two responses. Okay, so we can say that x complete or x whole is actually x free response plus, I'm sorry, x of the forced. Right, over time. And we can actually see it very easily if we apply the Laplace transform. But here, actually, for that matter, I don't need to resolve the system. I can simply take the solution that I wrote previously for this value, for this term, and add the solution that I obtained previously for the forced response. Okay, I have now don't have them written down, but you can actually add them together, and what you will obtain is the response under both input and initial conditions. And you can actually see that very easily if you apply the Laplace transform here, you will obtain this s of x of s minus x0 plus 3 times x of s equals u, oops, I'm sorry, u of s. And now let's factor together the terms. This is equal to 1, so it's 1 plus u of s. And now we will obtain this 1 s plus 3 plus u of s over s plus 3, right? And you will actually see that these two terms are the exact same terms that I obtained in my previous slides. So pretty much if I apply the inverse Laplace transform here, I will obtain the exact same solution, which is the summation of the two solutions found previously, right? Also, it is very important to note that, look at this denominator in both cases, I don't, before I replace the Laplace transform of the input, this denominator is like the same, okay? So this is the same, both for the free response and for the unforced response. I'm sorry, both for the free response and for the forced response, right? This is very important a bit later when we are going to discuss about stability, okay? So let's also plot the solution. Basically, the solution here is going to be the summation of the two previous solutions. So the system now starts at position 1, and as we saw earlier, it's going to end up in around here, which is 1/3, right? So this graph is practically the addition of the previous two graphs. The system will start from 1, and then without performing any oscillation, it will steadily go to 1/3 and stay there. I'm sorry. All right, just like that. Okay, so that's it about forced and unforced responses. Of course, we are gonna start solving a lot of exercises using the Laplace transform. So this is just, something to get your hands on. Any questions that you have, you write them down in the comments, and I will reply to all of them, and I'll see you in the next video. Thank you very much.